Uh, in this video, we will be discussing about another algorithm which is used in the cryptography. Uh, of course, in the continuation of symmetric cryptography, this is the second algorithm after data encryption standard or the DES. Uh, Advanced encryption standard was taken the place of data encryption standard, that is DES, and that is why it is known as advanced version of the data encryption standard. However, AES is very different from DES, uh, and the name has been given uh, just because that it is an advanced form of the cryptographic algorithm after DES. Now, this advanced encryption standard was published by National Institute of Standard and Technology, that is NIST, in 2001. Uh, and when DES was in operational, uh, people came to know about the vulnerability of the DES. That is why it has been considered that why not to develop another algorithm which cannot be cracked, and that is why the advanced encryption standard come into the picture. Of course, this is the algorithm for which many people have been asked, many countries has been asked to join a conference to give an algorithm which is more strong, more secure, more cost effective than DES. So they have created a conference. They have, and in that conference, 21 entries were there, out of which 15 entries were selected, which is going to fulfill the requirement of the conference. After that, the second conference took place, and out of 15, 5 were selected. And later on, in the third conference, uh, out of 5, the one entry has been selected, and that name of that algorithm was Rendon. And later on, it has been given the name Advanced Encryption Standard. This is being developed by 3 Belgian researchers, John Damon, Vincent Richmond, and uh, so based on their name, the name of the algorithm has been given. It is Raindoll, and after that, the advanced encryption standard has been given the name of that algorithm. Now, this advanced encryption algorithm is a little bit more safe than the DES algorithm, and it is being now used often in the symmetric cryptography. As I told you that it is a symmetric key cryptography, and it is being published by National Institute of Standard Technology in 2001. Of course, it is developed to overcome the vulnerability of the DES, and there are certain criteria, and based on that criteria, the AES was published, developed as well as published. The first criteria of the AES was the security. If you remember, in DES we were using 64-bit of the plain text and the 64-bit of the key. But as we know that with the advent of the technology and the advent of the fast computers, people came into the to have an idea that 64-bit key can be cracked. So why not to have the number of keys to be more than 64, and that is 128, 156, 192, and 256-bit key. So as far as the first criteria is concerned, it is the security. The second criteria is the cost. What is the cost means? It means the computational efficiency of the algorithm as well as the requirement of the storage of the algorithm is concerned. And the third criteria was its implementation, meaning the way implementation means algorithm must be flexible enough for it should be flexible enough, it should be simple, and it can be used in any kind of platform. It can be implemented in the hardware, it can be implemented in the software, like that. So based on these three criteria, the one algorithm has been selected which suits well, and it is going to overcome all the requirement whatever is being asked to overcome the uh, uh, whatever is the shortcomings of DES or the vulnerability of DES is concerned. So let us now discuss about the general design of the AES encryption, because now, as I told you earlier also in the previous videos, that DES is a kind of an algorithm which uses Feastal cipher, which has invertible, self-invertible as well as non-invertible elements. But AES is a kind of algorithm which uses only invertible elements. So the general design of AES is that AES encrypts as well as it decrypts the data blocks of 128-bit, which is more than the DES, in which we were using only 64-bit of the data blocks. Now we have three versions of AES. It uses 10 rounds or 12 rounds or the 14 round, depending upon the data block with which we are doing encryption and the decryption, as well as the size of the key which we are using. The third one is the key size can be used in AES is 128-bit, 192-bit, as well as 256-bit, depending upon the round. If we are choosing 10 rounds, then we will be using 128-bit. If we are choosing 12 rounds, then we will be using 192 bits. And if we are choosing 14 rounds, then we will be using 256 bits of the key. So it depends that what size of the key is being selected, and depending upon the number of bits selected as the key size, the number of rounds will be selected. As well as the beauty of AES is the encryption and decryption algorithm is same. Of course, the round key is applied in the reverse order. Of course, the same thing also applies in the DES also, that if you remember in DES what we used to happen, we are applying the round key and we have 16 rounds, and for each round we are generating 16 sub keys. And while doing the encryption, we will be using the sub keys from the in the ascending order, that is first K1, K2, K3, K4 up to K16. But whenever we are doing the decryption, we will be using first key as K16, then K15, and the last key will be K1. This is the general design of the AES encryption cipher, in which 128-bit plaintext has been selected to be encrypted. And the number of keys which are being used depends upon the rounds. If there are 10 rounds, we are using 128. This has been already explained. So in this general description, you can see the 128-bit plain text. Now, 128-bit plain text is, first of all, we are going to do the pre-round transformation. And for the pre-round transformation, we will be using a round key, and that round key is of 128-bit. Meaning thereby 128-bit plain text is transformed with the help of 128-bit key. Of course, this key which is being generated, whatever we have selected as 128-bit key, out of that one first round key is, and this is pre-round transformation, and after that we will be having number of rounds. If there are 10 rounds, after the pre-round transformation, we used to go with the 10 rounds, and then finally we will be getting the 128-bit ciphertext. So, meaning thereby, if there are 128-bit key, then there will be 10 rounds. But one round is being used as a pre-round, so total number of the key required for the AES encryption will be 10 plus 1, that is 11. So let us see how it happens. What is pre-round transformation, how the round number 1 is being done. In round number 1, what kind of activity is being done. In round number 2, what activity is being done. And the last round, what activity is done. Of course, you can see in this particular flowchart, in this illustration, that last round, which is written as round NR, it is slightly different. Slightly different, that will be clear later on. If you remember, please remember this, so that whenever we are discussing what happens in the last round, that will be more applicable. So 128-bit plaintext is converted into 128-bit ciphertext, but before that, if we have to go with the pre-round transformation, and then either 10 rounds, 12 rounds, or the 14 round, depending upon the size of the key which we have selected. Now, before going into the detail of the AES, let us discuss about some prerequisites which are required to understand the AES. The first is the data units. Now, we have 5 kinds of data units which will be used in AES. The first one is bit. Bit, you already know that bit means binary digit. It is a single digit that is either 0 or the 1. Whenever we second data unit is the byte. Byte is a group of 8 bit which is treated as a single entity, either in the form of a row matrix that is 1 cross 8 or in the form of a column matrix that is 8 cross 1. The third data unit is the word, and that word consists of 32 bits. It's a group of 32 bit, and that 32 bit is considered as a single entity, either in the form of a row matrix or in the form of a column matrix, and each row matrix will be having 4 bytes or column matrix will be having 4 bytes. So bit is individual binary digit, that is 0, 1. Byte is 8 bit but considered as either in the form of a row matrix or in the form of a column matrix. And word is a group of 32 bit. It is also considered either in the form of a row matrix of 4 bytes or in the form of a column matrix of 4 bytes. The fourth one is the block. Block is nothing but it's a group of 128 bit, which will be represented in the form of a row matrix of 16 bytes. Now you know 1 byte is equal to 8, so 16 into 8, that will be comprising to the 128. So these are the 4 data units, and the last data unit is the state. A state is just like a block, but states are normally represented in the form of a matrix, and that matrix is a 4 by 4 matrix in which the first uh, uh, value of that block will be in the state. States are represented, as I told you, in the form of 4. I mean, there will be 4 rows and 4 columns, and the states, as I told you, that it is represented in the form of a matrix. It is simply the conversion of the blocks into the state. So nothing is different from block to the state. Block is either in the form of a single row matrix or in the form of a column matrix, but a state is a kind of a matrix which is represented in the form of a 4 cross 4, 4 rows and 4 columns. Occasionally, a state is treated as a row matrix or in the form of a column matrix. And whenever we start doing the encryption process, or we are going to do the decryption process, the bytes of the blocks are first inserted into the state, column by column, and each column from the top to bottom. So there is a certain procedure how to convert the block into the state. Whenever we are converting the block into the state, we consider column by column and each column from top to bottom. So if we have to insert 16 bytes into the 4 by 4 matrix, we will first fill the first column, then second column from top to down, then the third column, then the fourth column. So there is a certain procedure of filling the blocks into the state, and there is the way by which we are converting the blocks into the state. The same way we will be converting states back to the block. So the way it has been converted from block to the state, the similar way we will be extracting the values from the state back to the block. So this is a general description of the data units in the form of an illustration. That byte, if we consider byte, byte can be represented, byte is a 8-bit. So 8-bit can be represented either in the form of a row. This is a row representation. This is the column representation. Then we have a word. Word will consist of 4 bytes, B0, B1, B2, B3, either in the form of a row or in the form of a column. Block is a combination of 128-bit. So 128-bit means 16 bytes. 16 bytes can be represented in the form of a block, either in the form of a row or in the form of a column. This is row representation of the block. And now the state. State is simply the representation of these block values into the 4 by 4 matrix, and you can see it very clearly that the first value of the block is represented as 00, then S10, S20, and S30. And this S00 is nothing but B0, S10 is B1, S20 is B2, and S30 is B3. So whenever we are converting block into this state, we are taking column by column from top to down. Then the B4 value will be considered as S01, S11 is will be B5, and so on. And this state can be considered as considered in the form of a 4 data words, where S00, S10, S20, and S30 is considered as W0, 32-bit. W1 will be S01, S11, S21, S31, that is W1. W2 is S02, and so on. So state can be represented in the form of a 4 words. Individual word are of 32-bit. So ultimately, the block size is 128-bit and the state is also 128-bit. Either we are representing in the 4 by 4 matrix, or in the we are representing in the form of a 4 word matrix. This is a process by which we can convert the block to the state and state to the block. There is a simple formula. You can see the formula of converting, that how the values are being inserted. Now, Si mod 4 comma I4. Now first one is representing the row and second one is representing the column, as depicted, illustrated in the previous slide. So Si mod 4, I by 4. So it means if I value is 0, so if I is 0, so that will be S0, comma, I is 0, so S00. And that S00 will be equal to block 0. It means B0 will be S00. Then when the I is 1, so 1 mod 4 will be equal to 1, and 1 divided by 4 will be equal to 0. So it will be B1, then B2, then B3. So B0, B1, B2, B3 will be the first column, B4, B5, B7 will be second column, B8 to B11 will be third column, and B12 to B15 will be the fourth column. And the way how it is being inserted and the same way it is being extracted. So this is how the block to this state and the state to block transformation is being done. Now, how the plain text is being converted into this state. So we will be using the same fundamental, that representing the ASCII value of the individual characters which are used in the computer. So A is represented by 00. Of course, A will be represented by 8-bit, and that 8-bit number can be represented by 2 hexadecimal digits. So whether we are representing it in the form of a 8-bit or we are representing it in the form of a hexadecimal, 2 hexadecimal digit, it doesn't matter. But the matter is, if we are representing hexadecimal digits, it is easy to handle. Instead of handling 8 binary digits, it is easy to handle 2 hexadecimal digits. Of course, the overall value is same. So whatever A, E, S, this is the plain text, and corresponding to the individual characters, we have find out the hexadecimal value. Of course, it is being converted into ASCII code, and then it is converted into hexadecimal value. And how this will be placed in the very similar 00, 04, 12, and 14 will be in the first column. 12, 04, 12, 00 will be in the second column. 0C, 00, 13, and 11 in the third column, and 08, 23, 19, 19 in the fourth column. Now this is the structure of each round at the encryption site. Of course, whatever general structure we have defined, in that general structure I have stated that there is 128-bit input, and it is pre-round transformation, and then round number 1, round number 2, round number 3, and so on. So this is going to give you the idea that what is happening in each round. So first of all, whatever 128-bit, it is converted into a state. And once it is converted into a state, that is a 4 by 4 matrix, it is applied with the first transformation, and that first transformation is sub-byte transformation. It means there is certain, using a certain table, we are substituting. The sub-byte means substitution of bytes. In this, we are doing byte by byte substitution. As in the case of DES, we are doing bit by bit transformation or substitution. In this, we are using byte by byte transformation. So individual bytes which are the part of the state is substituted so that this state is changed into a new state. This is subbyte is the first transformation. And after first transformation, applying the substitution of bytes, we are getting another state. Now, after getting this state, this is the second transformation is applied, that is shift row transformation. In this, we are shifting individual rows. And after doing shift row transformation, that is the second transformation, we will be getting another state. This state is applied to the third transformation, that is the mixed column. So we have a certain process by which we are mixing the columns, and so we are getting another state. And after this output which we are getting in the form of a state, then only the round key is being added. And then finally, whatever we are getting, that is the ciphertext. So it means in each round, we have 4 transformations. First is subbyte, that is substitution byte. Second one is permutation, that is the shift row transformation, in which the bytes positions are changed. Then we have a mixed column, in which we are doing certain process by which we are mixing the columns, and then we are adding the round key. One thing which you have to be add round key is applied before the first round, that is pre-round transformation, and third transformation will be missing in the last round. Suppose we have 10 rounds, pre-transformation round को लेने के बाद that will be 11 rounds. So pre-transformation round is over, first round is over. In first round we will be applying this sub-byte transformation, shift row transformation, mixed column transformation, and add round key transformation. But in the 10th round, which is the last round, if we are considering that number of rounds are 10, then in the 10th round, this third transformation, which is the mixed column transformation, this will be missing. That will not be used. Now the structure of each round, let us now discuss. However, I have already discussed. Each round uses 4 transformations except the last round, in which only 3 transformations are being used. And each transformation takes a state, create another state to be used for the next. And the pre-round section uses only 1 transformation, that is add round key. And the last round uses only 3 transformation, and a mixed column transformation is missing from in that. Now we start how the transformation is being done. The first transformation is subbyte. But before we go into the subbyte, let us understand what is the substitution. Actually, the meaning of subbyte is substitution of bytes. So how substitution is being done? Substitution means substitution is done for each byte. Please remember that substitution, whenever is done, it is done each byte. And for doing the substitution, we use a table. For doing that transformation, we use 1 table only. So if 2 bytes are same, then transformation will also be same, because for every kind of transformation we are using only one and only one table. So if two input bytes are same, that transformation will also be same. So what is subbyte? Subbyte, as I told you, that it is the first transformation, and bytes are considered as 2 hexadecimal digits. The left digit defines the row, and the right digit defines the column of the substitution table, and the row and the column junction points gives the new byte. So this is 16 byte to byte transformation called intra-byte transformation. Why it is called intra-byte transformation? No other value is substituted. Only the values which are available in the table will be substituted in place of a byte. And how and what table is being used? Before we go into the detail of the table, this is simply showing you, this is the illustration in which it is representing the subbyte transformation. Suppose we have this value has to be transformed. Now this value is AB16. 16 means hexadecimal number. A is a hexadecimal number, B is a hexadecimal. A will be representing row and B will be representing column. So in this table, A16 row and B16, the junction point is suppose CD, then this value is will be placed on this. So in this way, all the 16 bytes, all the 16 values, all the 16 bytes are transformed into different 16 bytes by using a table. And this is the table. This is column and this is row. Suppose we have the value is 5, 6. So row is 5 and column is 6. So that 5, 6 will be replaced by B1. Suppose the value is C, D. So C is the row and D is the column. So C, D will be replaced by BD and so on. So this is the first transformation, which is called sub-byte transformation or substitute byte transformation table. Using this table, we are substituting all 16 bytes by another 16 bytes. For example, we have this 00 and this 00 has been converted into a 63. How it is possible? Now this is 0, this is 0, so 63. So that is why 63 has been. Let us see what is the substitution of 12. Let us go to C12. 1 is the row and 2 is the column. So C9. So it is replaced by C and so on. So the way we are doing the encryption by substituting byte, we will be using inverse substitution byte in case of decryption. And for that, we will be using a table. And that table is the inverse byte transformation table. See, so this is how the sub-byte transformation takes place. Then the second transformation is the shift row transformation, and shift row transformation is related with the shifting of the bytes, and shifting of the bytes is a fundamental which is known as permutation. Permutation means changing the position of the bits. So in this we are not changing the position of bits, we are changing the position of bytes. So purpose is to permute the byte, and permutation is done byte-wise instead of bit-wise. And only one table is used for this transformation. So if 2 bytes are same, transformation will also be same. So that transformation in AES is known as shift row transformation, which is the second transformation. And shifting is done row-wise to the left. The number of shift depends how many bytes will be shifted. It depends upon the row number. We have 4 rows in the matrix of the state. 0 row, first row, second row and third row. Meaning thereby if it is row 0, no shifting. If it is row 1, 1 byte will be shifted. If it is row 2, 2 byte will be shifted. If there is, if it is third row, 3 bytes will be shifted. So it means row 0 is not shifted and row 3 is shifted 3 bytes. So this is how the row is being shifted. This is the illustration. Row 0, no shift. Row 1, 1 byte shift. Row 2, 2 byte shift. And whatever shifting is done, it is done left side. So this is how the last 3 rows are cyclically shifted. See the illustration. See, this is the original one. And whenever we have to shift, let us discuss about this is row 0, so no shifting is done. But it is row 1, so 1 byte is shifted. This is row 2, 2 byte will be shifted. This is row 3, 3 byte will be shifted. And how it is done. So this is how the shifting is being done. You see, in the row number 1, 1 byte is shifted. This is row number 2, 2 bytes are shifted. And this is row number 3, so 3 bytes are shifted. So shift row transformation is very simple. This is the example which has been shown. This is row 0, so no shifting is done. But this is row 1, so F2 is circularly shifted left side, so it will be coming over here. So F2, 63, 26, and the last value will be F2. Now this is row 2, so 2 will be shifted. So it will become 7D, D4, C9, and C9. And this is row 3, so 3 bytes will be shifted. So D4, FA, 63, and 82. Now the third transformation is the mixed column transformation. But before going into the detail of the mixed column transformation, let us discuss what is the meaning of this transformation. Now this transformation is an inter-byte transformation. If you remember, I have discussed about the first transformation, that is the sub-byte transformation, and I have told you that it is an intra-byte transformation, and this is intra-byte transformation because we have a table, and whatever values has been placed in that table, only those values will be used. But this is inter-byte transformation, so whenever we are mixing anything, any value from outside can come and replace the value of the byte. Now, purpose is very simple, is to mix the bytes to create a lot of confusion so that any attacker wants to know why it has been done, how it has been done, what is the key value. It is very difficult. Now, the mixing changes the content of each byte by taking 4 bytes at a time and combining them to recreate a new 4 byte in the form of a column. It guarantees that each new byte will be different even though if the all 4 bytes are same, because we are mixing is being done by the interbyte transformation. So interbyte transformation is a kind of transformation if the bytes are same even though you will be getting the different value. The combination process first multiplies each byte with a different constant and then mixes them. So this is the mix column, which is the third transformation, and how it is being done. It operates at the column level, meaning thereby one column is taken at a time of the state. It transforms each column of the state to a new column, and then transformation is actually nothing but it is a matrix multiplication of the state column by a constant square matrix. And multiplication of byte is done in the Gaulish field, that is 2 to the power 8 with the modulus value, that is x to the power 8 plus x to the power 1, and then adding is same as the XORing of the 8-bit world. So since we are in need of interbyte transformation, that changes the bits. So how it is being done, we are considering the value it as this is the state, and this state is going to be changed, and whenever we take A, B, C, D, so we are doing A, B, C, D and E, F, G, H, I, J, K, and then we take the X, Y, Z, T of the old matrix. This is the constant matrix which we have to consider. Now this constant matrix, whenever it is being considered by the sender, this matrix must be known to the receiver also, because if we are using a constant matrix for the multiplication at the encryption side, we must use inverse of this constant matrix to multiply at the decryption side. So this is how it is being done. If we have considered this matrix as the constant matrix in the encryption side, this is the inverse of this matrix which has to be done at the decryption side. So how this mixed column transformation operates, we have a constant matrix. This constant matrix has to be assumed by the sender, and it must also be known to the receiver so that it can take this inverse of this constant matrix whenever it is going to decrypt the message. So what is being done, suppose this is the column which has to be mixed. So what we will do, we take this column here, and this may multiply this column with this constant matrix, assumed constant matrix, and whatever is the resulting column which we are receiving, that is going to be replaced in place of this. So this is the input state and this is the output state. So the output state is going to change because this column is being multiplied by a constant matrix to get a new value, and this new value is replacing the older value. So this is the mixed column, how we are going to do. 63 has been 63, F2, 70 and D4 has been replaced by this one. This value is replaced by this one. And similarly, we are doing inverse mixed column in the decryption side with the inverse of the, with the help of inverse of the constant matrix. The fourth one is the key adding process. This is the fourth transformation. After doing subbyte, after doing shift row, after doing mixed column, the fourth transformation is the key adding process. But what is this key adding process? And this is the most important transformation. So what we are trying to do, AES uses a process called key expansion to create the round keys. Since we have 128-bit key, so what we are trying to do, we are trying to create 11 keys. Why we are trying to create 11 keys? Because one key will be used in the pre-transformation round and 10 key will be used in the 10 rounds. If we are using 12 rounds and 192-bit key, then in that case, we have to create 13 keys, one for the pre-transformation and the 12 for the round process. So we are considering right now that we are taking 128-bit long key, and this 128-bit long key, so we will be using 10 rounds. So total number of the key which is required is the 11. Now this 128-bit long key is considered as a 432-bit word. 432-bit word. 432-bit word is equivalent to 128-bit. Now, for the purpose of adding the keys to this state, each word is considered as column matrix. Each word is considered as a column matrix. Please remember this particular point. This is very important. So, how it is being done? How the key adding is being done? One column at a time. So, one column at a time. We will take this column, suppose, then we will add the keyword, and then whatever is the value which we are getting. Of course, this summation is nothing but it is the XOR operation. XOR operation of this byte with this byte to get this byte. XOR operation of this byte with this byte to get this byte. And similarly, this column added with the keywords getting a new value, and this new value is replaced by the replacing the older value. So for this particular purpose, we will be requiring the key expansion process, because we have only 128-bit key, but we have to find out 11 different keys. How we will be getting that? So key expansion is a process of creating the round keys for the different round, and for each round we will having different key. If the number of rounds is NR, as explained earlier, the total number of the key required will be 10 plus 1, that is 11. The first round key is used for the pre-round transformation, and remaining is used for the last transformation, that is round 1, round 2, round 3 and round 4. So the routine, we have a certain routine by which we are creating the round key, and these round keys are created word by word, whereas a word is an array of 4 bytes. So since we are creating round keys and round keys are created word by word, so the total number of the words which has to be created will be 4 into NR plus 1, that is 44. If NR is 10, then 10 plus 1 11, 11 into 4, that will be 44. So we have to create 44 words of the key by 128-bit key. So this is how we have a 128-bit key. Each word is of 32-bit. So the original 128-bit key in the form of these 4 words W0, W1, W2, W3 is used as it is in the pre-round. But with the help of W0, W1, W2 and W3, we have to create 128-bit key in the form of W4, W5, W6 and W7 for the round number 1. Similarly, we have to create W8, W9, W10 and W11 for the round 2 and so on. And how we will be creating these words, because W4 will be created with the help of the previous words, W5 will be created with the help of previous words, W6 will be created with the help of previous words and so on. So there is a formula by which we are able to create it. The formula says that Wi for I is equal to 4 to 43 are made as follows. How it is? We have to create W4 because we know W0, W1, W2 and W3. And what is that? The original 128-bit key. original 128-bit key is divided into 4 parts: 32-bit, 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 32-bit. So whatever is the original first 32-bit will be W0, W1, W2, and W3. So we need not to create the value W0, W1, W2, and W3. We need to create W4 to W44. So W4, how? The formula is, suppose we want to create W4. So W4, I is equal to 4. If I, Wi, so W4. So I is equal to 4. So 4 mod 4 is 0. If 4 mod 4 is 0, then we have different formula. If suppose I is equal to 5, so the 5 mod 4 is equal to 1. It is not equal to 0. In that case, W5 will be equal to W4 XORed with W0. It means W4 and W0 will be used to create W5. Similarly, if I is equal to 6, then W6 will be equal to W5 XORed with W1. It means W0 and W4 is being used to create W5. W1 and W5 will be used to create W6. W2 and W6 will be used to create the W7 and so on. But what about 4, W4, W8, W12 and so on? We have different formula. And that formula is, if I mod 4 is equal to 0, suppose we want to create the value of W4. It means I give value 4. So 4 mod 4 is equal to 0. Then in that case, W4 will be equal to T. We don't know what is T. T XORed with W0, where T is the temporary word, and this temporary word is the result of applying two routines, that is subword, rotate word on Wi minus 1 and XORing the result with a round constant, that is R constant. Now, we know W0, W1, W2 and W3, but we have to calculate first W4, because W4 and W0 will be able to create W5. But how to create W4? So for W4, we have to use this formula. This one. And W4 can be obtained with the help of T XORed with 4 minus 4, 0, XORed with W0. So what is T? T is simply using two routines: substitution word, rotate word, rotating of word of what? W4 minus 1, W3. So W3 is first rotated and then it is being substituted and then it is XORed with the R constant value. We have 10 constants, because if I is equal to 4, so R constant 0. For round 1, I will be 4, so it will be I is equal to 4, so it will be 0. So we will be considering R constant 0. What is R constant? We will be coming R constant later on, but to create W4 value, we have to calculate first T. So how T is calculated? And for the calculation of T, we have to know what is rotate word. Now this routine is similar to the shift row transformation, but it is applied only one row at a time. It takes a word as an array of 4 bytes and shift each byte to the left with wrapping, means circular shift. What is subword? Subword is similar to the subbyte transformation, but it is applied to the only 4 bytes. And the routine, each byte in the word and substitute another byte for it. So first of all, we will apply the rotate word, then we apply subword, and then it is XORed with the constant value. And these are the constant. And for each round, the constant remains constant. For round 1, we will be using this constant. For round 2, we will be using this constant. Which constant? R constant. For round 3, we will be using this constant. R4, we will be using this constant, and so on. So this is how, this is the illustration of key expansion process. This is W0, this is W1, this is W2, and this is W3. And this is a key of 128 bit which we have considered at the sender side. So this is W0, W1, W2, and W3. So how to create W4? W4 can be created, but W4 is a value which is W4 is a value which is processing of W0 and then XORing with T4 to get W4. And what is this one? This value is Wi minus 1 is equal to rotate word. First we will rotate. First what we will do? We will take W3 I minus 1. When we 4 minus 1 to W3. W3 is first rotated. Then it is substituted, and whatever output is after the substitution comes, it is being XORed with the constant value to get the value of T. And once you are getting the value of T, then this T is XORed with W0 to get W4. Once you are able to know W4, you can find out W5 by XORing W4 and W1 to get W5. W2 and W5 are XORed to get W6. W3 and W6 are XORed to get W7. But whenever you have to create W8, W8 can be created by using W8 will, the W7 is first rotated, then it is substituted, and then it is added with the constant value to get T. And once you are getting T, it is XORed with W4 to get W8 and so on. So in this way, we are able to get 44 words or 11 different keys. Out of 11 different keys, first key of 128 byte is as it is, whatever is considered, and the rest 10 keys are being created with the help of the different words by the formula mentioned in the previous slides. Now this is the table shows how the keys of each rounds are calculated, assuming that 128 cipher key agreed upon the sender as well as the receiver. And suppose the value is this one. So if this is the cipher key which a sender is using, so this 24, 75 and A2 and B3 will be the first word in the round. Then 34, 75, 56 and 88 will be the second word. Then 31, E2, 12 and 00 will be the third word, and then 13, AA, 54 and 87 will be the fourth word. Now with the help of this, we have the constant value, R constant. We try to obtain W4. How W4 can be obtained? We take W3, first we rotate, then we substitute, and then after the substitution, we XOR this, whatever is the obtained after the substitution, it is XORed with this value to get W4. Once you are able to get W4, you can find out W5 with W1 and W4 to get W6 with the help of 2 and 5 and so on. So in this way, you are getting from W00 to W43 by the use of this formula. This is the overall illustration how encryption and the decryption process used to happen in AES. First of all, we take the plain text, we add the round key, we apply substitution byte, shift row transformation, mixed column transformation, and then we add round key. And then in this way we go on, and you can see in the last round mixed column is missing as it is mentioned previously. And after doing this, we will be getting a ciphertext of 128 bit. Now, whenever we are doing the decryption process, first of all, we are doing the add round key. Then we have inverse shift row, inverse shift subbyte, invert, add round key, and the round key which is being used, as in the case of encryption side, we are using W0 to W3 in the first round, previous round, and W42, 40 to 43 is the last round. But in case of decryption, we will be using these key in the reverse order. And again, the last round of the decryption process is again missing the third transformation, that is the inverse, that is the mixed column. So this is how the encryption and the decryption used to happen. This is the example of the encryption process. That is the input state, the pre-round transformation, what is the output state, and what is the round B. In the round 1, what is the input state? Whatever you are getting in the form of an output state of pre-round, that will become the input state of the round number 1. Whatever you are getting as the output state of round number 1, that will be the input state of the round number 2, and so on. And this is how this used to happen. We have input state, subbyte, shift row, mix column, and then the output state after adding the round P.